Good day, everyone. This is Jeans from AGHAMALAYAN, and today we're going to talk about momentum and impulse. So, the formula for the momentum is, so I'm going to choose the pen mode and change the ink color to yellow so it'll be more pleasing. So, the formula for the momentum is P. This is the symbol for the momentum. In other textbooks, it is designated as P with the arrowhead on top because it is a vector quantity. But regardless of that, it is equal to the product of the particles mass, which is m, and the velocity. So the unit for our momentum is kilogram times meters per second. Now we also have impulse, so it will stop the momentum, it will prevent the momentum, and it is denoted by J. In other textbooks, it is denoted as J with an arrowhead on top because it is a vector quantity. Now this is equal to delta P, and delta P, that is change in momentum, so that should be equal to mass times the difference between the final velocity and the initial velocity. Now delta P is also equal to the net force times delta T. Okay, so we will use these formulas for momentum and for the impulse. Okay, so let's try to grasp the concept by solving this sample problem of the many problems I'm going to give you later. Now feel free to pause the video if you want to solve it. So we're asked to find the magnitude of the momentum of a 10,000 kilogram truck whose speed is not given up here, so this will be 12.0 meters per second. Okay, so what speed would a 2,000 kilogram SUV have to attain in order to have the same momentum and the same kinetic energy? So letter A. We're going to use the formula for momentum, that is mass times velocity. The mass of our 10,000 kilogram truck, of course, is 10,000 kilograms. No conversion will be needed for that one. The velocity is given over here, 12 meters per second. Computing for that will give us 120,000 kilograms times meters per second. Simplifying that to 3 significant units, because in here we have 3 significant units, it will give us 1.20 times 10 raised to what number? 1, 2, 3, 4, 5. So the exponent will be 5 kg times meters per second. Now let's solve for letter B. So we're asked to find the speed that the 2,000 kilogram SUV should achieve in order to have the same momentum and the same kinetic energy. So first, we will use this formula again, but we're going to solve for V. Solving for V will give us P divided by M. Okay, and then the momentum, which is what we will substitute in letter P, will be equal to the momentum of the 10,000 kilogram truck. So that is 120,000 kilogram times meters per second. Now the mass here would be, of course, of the 2,000 kilogram SUV. These units will cancel, and this will give us 60 meters per second. So this is the speed in order for the 2,000 kilogram SUV to attain the same momentum as the truck. Now, what about the kinetic energy? So first, we need to find the kinetic energy of the 10,000 kilogram truck. Okay, so K is always equal to 1 half mv squared, where m is the mass and v is the velocity. And then the mass over here would be, of course, since you're solving for the kinetic energy of this 10,000 kilogram truck, we're going to use the mass of the truck, that is 10,000 kilograms, and then the velocity of the truck is 12.0 meters per second raised to 2. Now that will give us 720,000 joules. So we will solve for V over here, and when you solve that using algebra, the 2 will go in the numerator and the m will go to the denominator, and then of course this square will be square on the outer side, so it will give us 2ke over m. Now this will be, then we're going to substitute the values. So kinetic energy of the truck is 720,000 joules, and then the mass of the truck, no, rather the SUV is 2,000 kilograms. Computer for that will give us approximately, since we're going to round the answer in terms of the least amount of significant units, it will be 26.8 meters per second. So that's it for this problem. Okay, now let's solve this problem about momentum. Feel free to pause the video if you want to solve it. So the problem states that in a certain man's track and field event, the shot put has a mass of 7.30 kilograms and is released with a speed of 15.0 meters per second at 40.0 degrees above the horizontal over a man's straight left leg. What are the initial horizontal and vertical components of the momentum of the shot put? So, of course, we're going to use the formula for momentum, that is P equals mass times velocity. Now we're going to draw the free body diagram of this problem. Now we know that the shot put is released this way, so the velocity is 15.0 meters per second. Then the angle is 40.0 degrees. Now for sure the x component of the velocity, if we're going to use SOHCAHTOA, will be 40. Oops, I'm going to erase that one. That will be 15.0 meters per second ka, so adjacent over hypotenuse, that will be cosine 40.0 degrees, because the x component is the adjacent side of the angle. Now for the Vy, the y component of our velocity will be 15.0 meters per second. This time, since this is the y component of the velocity, this will be sine 40 degrees. Now we're now ready to solve for the initial horizontal and vertical components of the momentum. So just going to change the color so it will be easier for us to identify what we are going to solve. Okay, so the x component of the momentum would be mv cosine theta. That will be 7.30 kilograms. That is the mass of our shot put. Then this one 15.0 meters per second, the cosine 40.0 degrees. Now computing for that will give us approximately 83.9 kilogram times meters per second, our unit for the momentum. And why 83.9 is our answer? It is because the practice is to express your answer in the least significant units. So as you can see in our problem, the least significant units is 3. Now we're going to solve for the Py. That will be mv sine theta, and then that will be 7.3 times 15 sine 40 degrees, and then computing for that will give us 70.4 kilogram times meters per second. So that's it for this problem. Okay, so now we're going to solve a harder problem about the momentum and impulse. So in here, we're asked to find the impulse and force that Big Bill exerted on the tennis ball in his record serve. Now in here, if we're going to read the problem, we're going to use the formula for impulse. Now the formula for impulse is mass times the difference between the final velocity and the initial velocity. Now the mass is has a unit of grams, so we need to use dimensional analysis to convert that into the SI unit that we use, just kilograms. So this is equal to 0.057 kilograms. Now substituting that, the values given in this problem in this formula, we will have 0.057 kilograms. VF, final velocity, is 73.14 meters per second, and there is no initial velocity given. So this is equal to 4.16898 kilograms times meters per second. If you're going to express your answers with the least significant units, it should be 4.2 kilograms times meters per second. Now let's solve for the force. So for the force, we're going to use the other formula, that is F net times delta T. Okay, and then solving for F net, we will have delta P delta T. Now for our delta P, since it is equal to the impulse, so that will be we will use the exact value, so 16898 kilograms times meters per second, and the time is expressed in millisecond, and if we're going to convert that into the SI unit of time, that will give us 30 times 10 raised to negative 3 seconds. Okay, and that will give us a value of 138 0.966 newtons, or simply 1.4 times 10 raised to 2 newtons. Okay, let's solve for letter B. So if Big Bill's opponent returned this serve with a speed of 55 meters per second, what force and what impulse did he exert on the ball, assuming only horizontal motion? So we're going to use the same formula. So J is equal to M times VF minus V naught. And then we will have here 0.057 kilograms, and then the VF will be negative since it is moving backward, it is returned to you, minus 73.14 meters per second. Now we are going to use our calculator to solve for that. 0.057 times negative 55 minus 73.14, that will give us negative 7.30398 kilogram times meters per second, or simply, if we're going to express your answer to the least significant figures in the problem, still in the problem, that will be negative 7.3 kilogram times meters per second. So this is your answer for the impulse. Now J is equal to delta P, which is also equal to F net delta T. Solving for the net force, that will give us delta P divided by delta T. And now we're going to use this value, the exact value, for exact results or accurate results, close results, or whatever. Okay, delta T will be, of course, the same time, 30 times 10 negative 3 meters per second, seconds rather. So I'm just gonna erase that. It's hard to erase that one. I don't know why. Okay. So now that it's all gone, this will be in seconds. Now dividing that, so 30 times 10 raised to negative 3, it will give us negative 243.46 newtons. When we're going to express our answers into the least significant units, that would be negative 2.4 times 10 raised to negative 2.4 times 10 raised to 2 newtons. Here's our answer for this one. Okay, so it is time to talk about the elastic and inelastic collision, as well as the completely inelastic collision. So in elastic collisions, let's say in an isolated system, it means that it has no friction or any other factors that could affect the system. The kinetic energy and the momentum is conserved. How do we illustrate that? So in elastic collision, okay, the ball is moving downward, it hit the ground, and then it came back up with the same kinetic energy and the same momentum when it first fell down. So the formula for that will be m1v1 plus m2v2 equals m1v prime 1 plus m2v prime 2. So the left side will be the initial velocities, and the right side will be the final velocities. So you can also symbolize this as MA VA1 plus MB VB2 equals MA VA2 plus MB, oops, this should be MVB1 MBVB2. So these are just the same equations. Now for inelastic collision, okay, the kinetic energy when it first fell down is less than when it came back up. So we say that is that one. So, and then there's another type which is completely inelastic collision. That is when you drop the ball, it will not come back. So the kinetic energy will be completely lost, and the ball will assume the velocity, the same velocity as the ground. So that is completely inelastic. And the formula for that, so we're going to change the ink color. The formula for that will be MAVA1 plus MBVB2 equals MA plus MB times V2. Okay, so we run out of space already. So let's first try to grasp the formulas by solving the problem, which is this one. So in the problem it is stated that there are two skaters that collided and grabbed onto each other on frictionless ice. One of them, of mass 70 kilograms, is moving to the right at 2 meters per second, while the other, of mass 65.0 kilograms, is moving to the left at 2.50 meters per second. What are the magnitude and direction of the velocity of these skaters just after they collide? So feel free to pause the video if you want to solve it. So first, we need to identify what kind of collision is this. So since they grabbed onto each other, so they have the same velocity, so it means that this is completely inelastic collision. So the formula for completely inelastic collision is MA VA1 plus MB VB2 equals MA plus MB V2. So solving for V2 will give us MAVA1 plus MBVB2 equals MA plus MB. Now we need to substitute these values now. So MA is 70 kilograms, VA1 is positive 2, MB is 65 kilograms. However, since it is moving to the left, so, and this is a vector quantity by the way, so 2.50 meters per second here will be negative 2.5 divided by 70 plus 65. Solving for that will give you negative 1/6 meters per second, and to express that in three significant figures, which this will be approximately equal to negative 0.167 meters per second. So that's your answer for that one. Okay, so we're going to solve this last problem, and this is about elastic collision. So let's read the problem. A 10-gram marble slides to the left with a velocity of magnitude 0.4 meters per second on the frictionless horizontal surface of an icy New York sidewalk and has a head-on elastic collision with a larger 30-gram marble sliding to the right with a velocity of magnitude 0.2 meters per second. Find the velocity of each marble, magnitude and direction after the collision. Now, since the collision is head-on, all the motion is along a line. Now, let's use the formula for elastic collision. So it is VA1 plus VB2 equals mass of A, plus VB2. Now mass A, we will refer to this one, is 0.03 kilograms and its velocity is 0.200 meters per second, plus MB is 0.01 kilograms. Now notice that we converted 10 grams into kilograms because we cannot compute with grams only because it is not the SI unit of mass. So let's assume, to solving the problem, VB2 is 0.400 meters per second equals 0.03 kilograms times the final velocity plus 0.01 kilograms VB2. Now let's add this one. It will give us 2 times 10 negative 3 kilograms equals 0.03 kilograms VA2 plus 0.01 kilograms VB2. So let's write that equation in here. 2 times negative 3 kilograms equals 0.03 kilograms VA2 plus 0.01 kilograms VB2. Now notice that we have two unknowns here, and there's no way we can solve this if we don't know the technique that I'm going to show you right now. So usually these kinds of problems usually give their the final velocity of one block, let's say this block or that marble, but in this case it isn't. So I'm going to share with you a technique. So I will label this first as the first equations, since we're going to use system of linear equations. Now I'm going to use a light green, no, not that, a white. So this equation, VB2 minus VA2 is equal to negative VB1 minus VA1, and this is the what you should remember when we have two unknown final velocities in the elastic collision equation. Now let's substitute the values. So it is this is negative 0.4 minus 0.2. This will give us positive 0.6 meters per second. Now our second equation will be VB2 minus VA2 equals 0.6 meters per second. Now I'm going to use a calculator to solve for this problem. There's a mode specifically designed for that, and the values that came out from the calculator are the following. So the x value, which happens to be my VA2, is negative 1 over 10 meters per second, and that is negative 0.1 if we're going to write this in 3 significant figures, because that is the least count of significant figures present in the problem. Now we're going to write this as negative 0.100 meters per second. Then VB2 will be equal to 1/2 meters per second, and when you're going to convert that into decimal places, then it will give you 0.500 meters per second. So these are your answers for this problem.